right? Do you have that video set up and ready to go? No?
No, but I can do that.
Actually, Senna, why don't you start? I apologize for the delay in getting this started. Senna, would you start first, and then we will have John's video second, and then we'll have Alan's presentation. Is that all right?
Yes, of course, I can start. Okay, first of all, welcome everyone. It's really nice to see so many people here. I'm really excited to share what we have done in this fall semester, actually. And actually, we continue with the webinars, and we have many great presentations going on in these webinars, and it's really an honor for me to present here today. And although I'm going to present alone, I was not alone doing the job. So I have really great teammates, and some of them are already here. For example, Meltem, Nihal, Emre, Ülkem, and also Büşra is here. So we were all working together in this project that I'm going to present. And we have more teachers and researchers involved in the project as well. So I will do my best to explain what we have done. I will just share a short presentation. So let me just share my screen here. Okay. So I will try to explain everything with the cards here, and also I will open up the models that we have used during the trainings. So our project is named Environmental Education with Systems Thinking and the World Climate Simulation Game. And as I said, there were many people involved in this project. Darüşşafaka schools from Turkey, Systems Thinking Association in Turkey, Boğaziçi University, and also UNDP Accelerator Labs. So we did this program together with the students in the 8th grade, and it lasted from September to December, and we did it after school with voluntary students and also with voluntary teachers. We divided the program into 3 parts, first part, second part, and third part. And in the first part, it was like a preparation for students to do the World Climate Change game. So I will start with the second part, actually, and then go with the first part and then the third part. So what is, maybe you already know what is World Climate Game. So it's a simulation game, it's a role-playing game, and students are in the groups, and they are actually role-playing the United Nations negotiations for climate change. We played the 6 group version of this one. So students were pretending like they are from United States, and they joined meetings and to discuss how they are going to proceed with their decisions related to the climate crisis. And we also had additional groups. So there were climate activists and Climate Alliance, fossil fuel lobbyists, and journalists. So they were also going to involve in at some parts to raise some issues towards the decisions. And in the beginning, there is an opening ceremony, and we are telling students that, yeah, our goal today is limiting the global warming to less than 2 degrees and as close as 1.5 degrees. And we are asking them, so you need to agree on a deal to share costs of mitigation and also adaptation fund to aid most vulnerable nations. So in the process, basically they are going into their groups, and they are formulating their negotiation strategy based on the questions presented here. And also then at some point they talk to other groups, and they also negotiate how can we find the best possible solution. And they prepare a brief speech, and they go there and they do their speech. And also when they decide how they are going to proceed with their, for example, they decide on their reduction date and deforestation prevention and also afforestation promotion. And all of the groups here write down their numbers and then see how the world will continue raising its temperature. And they are trying to reduce this temperature increase as much as possible. It took around 4 hours and we did this simulation game online. And it was really, really good in terms of teachers, like seeing students, how they are negotiating and how they are building their claims with the evidences they have. And this was really good because we had the first part, which was like a preparation for the World Climate Change game. So when we talk about environmental education with systems thinking, so we have a focus on climate change, but we didn't take it solely as an environmental problem. So we also considered the economical and also population related problems. So everything was kind of connected to each other, and we wanted to really prepare students for the negotiations here. So we started with explaining them how population works, how migration works, what is the basics of economy, and what is the relationship between emissions with all the other topics presented here. And I will try to explain it in this one. So it was like 4 weeks of preparation. And each week we try to cover one topic under these models. So we started with the population. Here you see like there is a stock flow diagram of population, and we just fix the deaths for any of them. They can just go any of the countries here and then just see how its population is going. But as you can see, the model is not working right now. So we ask them what can they change in the model so that their graph also will look like the real graph here. So for example, they needed to write the, let's go with the Turkey, for example. Oh, sorry. In the beginning, in 1960s, Turkey had around 20 million people. Oh, okay. And then also we need to change the birth fraction here. So they solve that all of the components presented here, how it actually affects the behavior of the population over the time with changing some of the parameters here. We didn't let them change everything. So for example, we gave them the actual death fraction all the time, but they could manipulate the starting point of the stock and also the birth fraction. So they just changed, they just looked for other countries and looked how their population is changing through the time. Then, of course, we cannot only stay here when we are talking about population, we cannot only stay with births and deaths. We also talked about how migration has an effect on a population of a country. And for this one, we, for example, looked for Syria. So we wanted them to try to explain what happened here and why there is a decrease here and what happened. Can you explain it with the stock flow diagrams here as well? And then we continued with the consumption part. So here we showed them how production and consumption cycle is working. So we are using natural sources and we are using them to produce some products. So we produce them in the fabrics, and then we distribute them to the markets, and then we buy them, bring them to our house, and take it to the garbage then. So we can either recycle them and go back to here, or we can do composting and we can go back to here. So it doesn't it doesn't have to be the case that every time we need to use the natural resources over and over again. So we try to explain it in this sense, and then we defined the GDP as the country's consumption amount. So if a country has a higher GDP, this means that this country is also consuming a lot. So we try to discuss these concepts in comparing them with other countries as well. And then we continued with the wealth. So in the, for example, let's go with Turkey, or in wealth, we brought population stock flow diagram here. So we still have the consumption production cycle and also the population stock flow diagram. And we explained what does wealth mean. So it is actually GDP per capita. And although some countries can have the same economic growth, but they may not have the same wealth because of their population. So for example, we looked for United States, and also we compared it with China. Although they have same economic growth right now, they saw that their wealth is not the same because of the population. And then we continued with the emissions, and we here explain that everything that we do, like just from natural resources to our houses, everything we do, it increases the emissions for carbon dioxide emissions. So every time we buy something, we are making a decision, not for the things that we are buying, but also if we are going to buy, if we are going to buy this stuff, that means that we are going to contributing carbon emissions over and over again. But then we go to the world, for example, here, as you can see that although wealth is increasing together with carbon emissions. So we ask them, isn't it do you think that it's not possible increasing our wealth without increasing carbon dioxide emissions? So would it be possible to do that? And how would it be possible? And for this one, maybe we can go to Germany. Okay, so there is an example of, although the GDP per capita continued to increasing, there was a decrease in carbon dioxide emissions. And how can we do this one? So we are looking back here in the recycle and composting rates. So we can find different solutions, and while we continue consuming or producing, if we use different energy sources, which does not contribute to carbon dioxide emissions, then maybe we can do this one too. So we need to decide on the energy resources that we are going to use for continue to grow. So this was the basic ideas presented in the first part of the education program. Then we had the negotiations. Then we continued with the foundational structures. And this was more focused on the scientific knowledge of students. So we looked at the carbon cycle, greenhouse effect, and we also had a small session on energy solutions. So how can we deal with the carbon emissions later on? I will go with the carbon cycle first. So we started with this graph. So something has happened here. So this shows the graph of carbon in atmosphere, its behavior over time. So something has happened here so that the carbon dioxide has increased after this time. And we talked about industrial revolution here a little bit. And then we continued with the what was it like before and what was it like after? We started with the carbon stock. So where does the carbon exist in Earth? We asked them, and we found those stocks. And then we asked them to connect, make the connections between those stores. So, and what are the events that makes this carbon move from, for example, soil to atmosphere, or deep earth to atmosphere, or oceans to atmosphere? So what happens in there? And this carbon is just going one place to another one. So before industrial revolution, as you can see, we built this one one by one with students. And when we ran, so we kind of try to find the equilibrium point. So carbon is going around on the Earth from different store to the other store, but there is an equilibrium. And what happened? So let's go back to problem. So this is the equilibrium part. So what happened here so that it increased? We just made a manipulation on here. So although carbon in deep earth takes a lot of time to go in the carbon in atmosphere, so as humans, like we just increase the emissions happening from here to here by burning fossil fuels. So this was, our aim was to explain them what is happening, like what we are doing and how it is affecting this model. So it was just opening up the flow rate from here. And
well,
they also, sorry?
Valve of the flow?
Yeah. And then after carbon cycle, we continued with a greenhouse effect. But for this one, first of all, we wanted students to understand really well how does how they are affecting the inflow and how the increase in inflow can affect stock. So if there is a factor that increases inflow, this one increases also the stock. So when they run, they could see like what is happening in here. So we just wanted them to understand really well the relationship between like the factor and inflow and the stock. And we go one by one. And then like here, it was the most difficult part, but we want them to understand it really well because this is actually like preventing this outflow to happen. So this is also what is happening in the greenhouse effect. So that's why we just gave a huge emphasis on this part. And then we continued with here. So we have carbon dioxide stores in atmosphere, and there are emissions and absorptions. And like we just gave the basics of the model, and we asked them how fossil fuel usage is affecting one of the stock flow diagrams here, and how greenhouse effect have an effect on those stock and flow diagrams. And then we continued explaining it in this way. So here, greenhouse effect is actually not contributing the heating flow here. It actually prevents cooling. And we try to explain it also with an insulation experiment. So we just had 2 cups with the one with a lid and one without lid. And they put the thermometer and try to monitor the temperature raise with a lid and without a lid. And we try to explain them like greenhouse effect is not giving actually an extra heat like sun is doing here. It is actually preventing Earth from cooling. So it is trapping the heat inside there so that heat cannot escape. So that is what is happening. And actually, when it is in the right amount, it is good for Earth. But yeah, what we are doing is that we are putting more on the emissions flow, and this one, atmospheric carbon dioxide is increasing, and this increases greenhouse effect, and this means that Earth cannot cool as the way that it cools. And lastly, we continued with En-ROADS simulation. So we asked students to take a look at all the energy supplies and transportation and building and industry growth, land and industry emissions, carbon removal, and try to figure out how they are affecting the temperature increase and what kind of decisions are contributing to this temperature to go down. So they were like trying to find out some solutions and how, and they base their solutions on the evidence that they had here. But maybe we cannot say that as a solution, but they were just like having ideas. How can we use our energy sources better so that we don't increase the carbon dioxide emissions in the end, so that we don't increase the temperature? And actually, like, this was the whole program. And after we finished the program, students wanted to continue with the second phase. So when we finished, they told us, can we continue meeting after school and do something about it? And we started to reading articles about the solutions they are doing for the climate crisis. And we want them to build this, like put these solutions in the frame of the models here, and how those solutions affecting the climate crisis, and like which flow it is affecting and how it is affecting. And also we put everything that we have done in on open training platform for teachers, so that if a teacher wants to do the same program as we did here, that teacher can just reach that course and look at the materials, and everything is included, the videos, everything is there. But for now it is in Turkish, and also the second phase is right now going on, is in Turkish. So actually that's all I'm going to say like today in this presentation. And I am looking forward to your questions and your comments, but I think it will happen after everyone presented, right?
Well, it was actually going to happen after each presentation, but I want to make sure, because it was 15 minutes for presentation and it's gone a little extra. And a lot of that is my fault for coming on late. I'm sorry, I was unavoidably detained, but what you have presented is so exciting. I think that this is wonderful information that you're sharing, and that when we can translate it to English, there will be a lot of interest, certainly in the United States, for using this material and this approach. But Sena, if you will allow, I would really like to optimize the fact that Alan is here, and John could not attend but gave us a video. I think I'll show his video last, because I want to make sure we give Alan enough time to present his information, and that we will take a little bit of time after his presentation for information. And we cannot show all of John's video in the time that we have left. Well, we'll just let people leave at the end of the hour, and if other people want to stay, they can stay to watch the end, because he won't be here for questions, but it will be recorded, so that will be available to everyone. So Sena, if you wouldn't mind, I'd like to ask Alan to present now, and then we'll have questions after Alan's presentation for at least 5 minutes. Okay.
Thanks, Diana. I'm going to share my screen. And okay, so I'll try to keep to my allotted time here. And if you don't have time for me to answer enough questions, there's my email. It's just my last name at gmail.com. And we have a website from the publisher of the recent book that we've put out. Now, I'm going to say we, just as Sena was saying, she's part of a team. I'm part of a team as well. I was the author on my own, but had tremendous amounts of editing help from Lee Stuntz, who's the publisher, and Anne Levine, who did the layout and also some editing. get to the next slide here. Okay, whoops, sorry. So I was working at Innovation Academy, a high school in Massachusetts, United States, and they moved some of their traditional, so to speak, science curriculum to an environmental science setup. And the differences in those two show here in this diagram where the intersection is where a lot of interesting stuff takes place. So that most environmental issues have components of all of those land, water, air, and sustainability issues. And in addition, we took the environmental systems part and then connected it to other issues that are in society, including social justice, public health, and the economy. And Senna talked a lot about that as well. There are some interdisciplinary considerations that always have to take place, and we've also tried to expand into other areas, so that a science class and an English and language class and a math class, so that they're not all just separate excuse me, classes. They can take on some of the similar issues involving the environmental systems. So in this talk, I'm going to quickly go through these particular tools, and I will give an example in a general sense of a big question in environmental science. Then I'll give an example that students in Innovation Academy studied, either a local one or some issue that they did research on. So there's big picture ones, and they're mostly from my book, and the others are from Innovation Academy. And I just want to say, rather than this being a shameless economic plug for the book, a lot of it is available on the website. You can check it out. So behavior over time graphs. We used with the students the 4-question format there, which you can see what's changing and what is the way it's changing, why, what are the reasons and the structures that are driving the behavior, and then what's the significance and what do you do? And that's where I got really interested in writing the lessons that I did for my book and taking the title, Now What? So here's one interesting behavior over time graph. This is energy sources in the United States. And you can see that coal, one of the nemesis that causes climate change, has gone down nicely, but the renewables are kind of slowly climbing. And while the percentage rate is changing and growing, it's still pretty low. So there's a behavior over time graph that helps kids to think about the energy problems that we have. This particular graph is how solar energy is produced from a single house, and this would be a sunny day, and around noontime, getting the peak energy, and then overnight, no energy from it. And the next day is a kind of a mixed cloudy and sunny day. So renewables have the problem of not being as steady sometimes. And we end up with this kind of curve, which is called a duck curve. It's kind of a nice thing to show kids that this is the load that is necessary to produce electricity. This is the solar production. And then this belly of the duck here is the difference you would have if you didn't have the solar, and you have to figure out how to make up for the times when the solar power is down. Now here's a local one that the students did. They took a field trip in their environmental systems class to a nearby beach, and these are Google images of what the beach looks like at the end of the summer. This was from October, and then after winter, this is from April. You can see how much of the beach has been eroded by storms and the normal waves action. And this slide shows the beach over time. Let me move this over, sorry, I think this is. Okay, the beach over time, and no matter what humans do, there's a natural migration on this part of the beach. This is Northeast United States, and the storms come from the Northeast and they push the sand down in this direction so that there's a migration. Of course, if you're a homeowner and you've invested a lot of money into your property and want to protect it, you try to look for solutions. And the students learned that battling nature doesn't usually pay off. And we'll come back to that in the next section. Here's the connection circle and causal loop diagrams. And these icons are ones that Anne Levine made up for us to use to show at the beginning of a lesson what systems tool is being used in that lesson. So I'm going to show a couple more examples, and I'll come back to the beach one, how the students use connection circles and causal loops. Here's a connection circle about smog in Poland, and when the government was working on trying to replace coal stoves for people to reduce smog. I used an example of an article reported in the New York Times about how that was going. And most of you are probably familiar with connection circles. Here's just a diagram of when the need for new technologies because of the smog happens. We can have a loop caused by these different factors. I'm not going to go through that one because we want to move to the local one, I think. So this student, that's not really connection circle. I think he or she was thinking along the lines of, well, what is going on with beach erosion, and the more beach erosion, then that causes property damage. And there's something called a riprap, which is a stone wall that people put up or other materials to try to block the waves from their property so that their sand isn't eroded. And what tends to happen is that it actually captures the energy in the waves. There's more waves, more turbulence, more intensity, and there's more flooding and more erosion. So you can see that then the person did that, the more beach erosion, the more building structures, and the more building of structures in that case, the more beach erosion. So it's a kind of a summary of unintended consequences there. The students studied river flooding, and I wanted to show some examples where, the kids aren't always doing these things perfectly. There's a lot of mistakes here, and I think it's important when we work with students to find and correct the mistakes with them. Some teachers, especially those who are new at using the systems tools and using system dynamics and systems thinking, tend to think if a student uses a diagram, well, it's okay. But here the polarity arrows are very confusing. This person, also they misspelled levees. Levees are walls that go along rivers to hold flood waters in when the river rises. So this person was saying that, as the more levees are built, there are fewer marshes and delta land, and that negative sign should have gone back here. And when there's less marshland and deltas, then there's fewer places for the water to go, and it increases flooding, and then tend to build even higher levees. And again, it's a reinforcing loop of, a proposed solution not getting done what wants to get done. And so there it is cleaned up and revised, that just as I explained, and put the polarity arrows, of course, the polarity signs near the arrowheads. Here's another one that shows, are people learning about it from these levees? And again, it's not very neat. There's an adjective used here, worse. If you end up having a causal loop and you walk around it and you say, well, it's less worse, you end up with some really difficult grammar for the people to understand. So there it's cleaned up again when there's more flooding and there's more building of levees. Marshland goes down, natural flood control goes down, and flooding goes up. Do we learn from that, or do we keep getting worse? So that's a more clear causal loop. And then this person told a story. It's on the way to a causal loop diagram. Scientists trying to outsmart nature. The kids they really like to see when the experts are wrong. And so the building of levees tend to actually increase erosion. So it's controversial. But again, people living right by the river, the levees often do save them. So it's sort of a short-term gain for long-term trouble. I have a couple of examples to show you of archetypes that we use. This is the drifting goals, also called eroding goals, and it's the archetype where there's a gap. So here's the example of carbon dioxide, and there's we all want to lower the amount of carbon dioxide being emitted, and so there's pressure to lower that. And I'm sorry, there's a pressure to get it done on this part. And the more actions that are done, the less carbon in the atmosphere, and we close the gap. But it's so hard to do that, and it's so costly that there's pressure to lower it. And then the target tends to either be ignored or reduced. And there's a template. Once we show students the archetypes, then to give them a blank template, they can take the problem that they're studying and put in their own variables. So what we did, we also had a climate summit similar to the one Senna was talking about, and in the afternoons we would give the kids a problem. So we used this template, and we talked about the problem of the rainforest being cut down for agricultural use. And so this is one of those goal gap situations. The one goal is a large and sustainable rainforest. That goal competes with the people who want a large agricultural area. And we end up with these two competing balancing loops. We also use iceberg diagrams. And there's a template. In our book, we decided to go with the 3-level iceberg and have mental models up along the side. Some people use 4-level ones with mental models underlying the bottom. I've even seen 5-level ones, so it's just a choice that you make, what you're comfortable with. Here's one that we used in the book to show about carbon emissions and behavior over time in the pattern level, and then a causal loop and a stock flow diagram there. And the mental model going along here is particularly for people in the United States, that owning and driving a car is a human right. In Innovation Academy, some of the students used other areas of their studies, and they were used to using the iceberg diagram. I just have 2 quick ones to show you of students learning Spanish, and as they're learning a different language from English, they're anxious about using it. So the teacher has them do interviews. That's the event up there, and as they go along in their years, they're 6th grade. I know, sorry, it's a little small. 6th grade, 7th grade, 8th grade in middle school. The intensity of the experience gets harder. They just have more things they have to do in their interview. And so this student said that as his I think it was a boy, his participation goes up, his motivation to contribute goes up, and his enjoyment of the class goes up, and he participates more. So he has a reinforcing loop there. And I have a second one where this student also drew a reinforcing loop as his fear went down. And his model was eventually that in class, the more he participates and pays attention, he gets better. This was a iceberg diagram about maple sugar production in the northern forests here. The maple trees have sap every spring, and the sap is tapped and boiled down. It boils down, then a syrup is made. And this teacher was studying the problem with her students of what's going on, that the sugar content is down, and they had some ideas in their iceberg diagram, and they went out and they tapped the trees and made their own syrup. Then with the students, she did a couple of causal loop diagrams, and the one on the left is about the sugar maple trees are not as healthy. They're susceptible to stress. That's a reinforcing loop, and climate change is a major factor, it's believed, on why the maple trees are stressed. And then in the diagram on the right, similar to the diagram at the beginning of this talk, there's an intersection of the environmental system in the atmosphere and the environmental systems on land. As the CO2 increases in the atmosphere, I'm sorry, I lost a bit of the screen there, but the climate change is occurring even more. Finally, I'll conclude with some stock flow diagrams that we used. Here's a diagram. Here's a diagram of recycling, or what happens with waste materials. And yeah, it's very complicated to just produce these for students when they're beginners, especially. And so a 5th grade teacher made up this very simple template for kids to use with the analogy of a bathtub. And so students, when they were making their stock flow diagrams, could write the name of the stock right across the bathtub, and the inflow on one pipe and the outflow on the other pipe. Using storytelling is a good method. It's showing parts of a diagram and revealing it a bit by bit. So here's the simple bathtub looking diagram of carbon dioxide in the atmosphere. And the next phase shows the stock of CO2 from emissions increasing and adding to the inflow up here. And this is the part, again, that Senna talked a fair amount about, where the heat's radiating into the atmosphere, but the carbon dioxide is slowing down the amount that can radiate back to space. And then there's no feedback left for the kids. They can say, well, now what? What's the implication here? Where can we find some leverage points in this diagram? Again, Senna covered this one, the carbon cycles and where carbon is on Earth, and drawing a fairly simple diagram so students can look at the stock and flow of the carbon cycle. And a more local example, which I'll end with, is students in a chemistry class were studying about addiction, and the problem of a lot of the students unfortunately knew friends or family that had fallen prey to addiction. And together, I worked with them on this one. We made a stock flow diagram of their perception of the problem. So the 2 stocks starting there, illegal drugs that are available in addicted people. And a lot of the drug enforcement was looking at the drugs entering the United States, and the illegal drugs that were available were causing people to become addicted, increasing the stock of addicted people. And as the addicted people would increase the demand, more illegal drugs, more drugs entering the country, more drugs available, and you have a reinforcing loop of an addiction crisis. Adding to it are pain medications that were really way over prescribed here in the United States, and that added to people becoming addicted and increasing this reinforcing loop. So that was really helpful for students to look at the stock flow diagram and then think, where are the leverage points? You know, is it really up here, or is it mostly the drugs entering the country? Is it here? Is it therapy for addicted people, or you know, many areas where would be the leverage points that a student would want to support? Here's a template for planning local or independent student projects, and again, that's right from our book, and that a lot of the parts that I've shown you are available for free downloads from the Creative Learning Exchange. But this is a good way for students to start with their issue here. What are the trends? What are some behavior over time graphs they can find about it? Some data that are important. What are the structures? Can they look at stock flows or causal loops or other systems tools that'll help them? Where's the leverage, and what's the action to take or support? And here's just a couple of addresses. I think through Diane, I can share some of these slides. I'm sorry for rushing through some of them, but we hope that at the Creative Learning Exchange, which is clexchange.org, people can share some of the work that you're doing, and we can start putting that up there to create more of a network. So thank you for inviting me and listening.
Thank you very much, Alan. I think the book is going to be a huge resource for teachers and for anyone interested in using the systems thinking tools and the system dynamic stock flow diagrams. It's extremely valuable on a topic that is important to everyone. So thank you very much for your presentation. I know it's 20 after. I think it's important to give you a chance to ask our presenters questions. And so we're going to take at least 5 minutes to do that now. And then I will show the last video, which will extend beyond an hour, but I'll just keep playing it. And those of you who can stay or watch it later on the replay. So please, any questions for Senna and Alan? Senna, do you know when the materials are going to be available in English for all that wonderful computer setup for what you had done?
You mean teacher trainings or the?
Well, both. Unfortunately, most of us would not understand the Turkish, so we're really excited to have it, but we'd like to know about when we might be able to see it in English.
For the models that I presented today, they are already in English, and actually I can share with everyone that the presentation that I had today, so that you can look at every models that I presented today, and the teacher training part, I don't know yet the time frame, but yeah.
Okay. Emre, do you have an idea when that might be, the teacher training part might be available in English?
Well, I think this is the second course that we prepared for the online course. The first one was Introduction to Systems Thinking, and we based our mentoring activities on this first one. And for the ones that completes this first course, we'll be able to have the second one, this about climate change one. So we are planning first to translate the first one, 101 Systems Thinking online course to English. I think in this summer, it will be finished, at least we're planning to do so. And after that, until the end of this year, we can do the second part, but this is just
so early next year then, probably. Yes. That teacher training. And all your teacher training online classes are free, correct?
Yes, of course.
Yeah, yeah. Yeah.
And they are also recorded by the teachers who actually use those models inside the classroom. So also, like, teacher trainers are also the teachers who did this program in the classroom.
Oh, great. That's really important, I think. Alan, your book has only just been out for a few, like a month, a few weeks. And it's available at the Creative Learning Exchange. And you said there are quite a few things that can be downloaded. Would you like people to let you know if they're using parts of your book in their teaching?
Yeah, that would be really nice. I'm hoping to, do some sharing on the website of lessons that people are doing. I'm also hoping to keep updating the book, since it's a lot about current events and things keep happening, and we're in the middle of a climate crisis for sure. So I would like to establish a blog and invite people to work with me on that and send work that they're doing and ideas they have and so on. I'll let people know about that, and if they check in on the Creative Learning Exchange, they'll see when that comes up.
If any of you have, oh yes, please, Stephen.
Yeah, I'd like to thank both of you immensely for the work you're doing. I think it's so critical. And it's wonderful to see you both using systems thinking and system tools. I have a kind of specific question. Both of the presentations today, and I know this is also for John's work, you both used stock and flow representations. And I just wondered, have you come across issues with that, with kids trying to take that kind of abstract representation and map it onto what their understanding of the real world is? And if you have, what kinds of ideas do you have about how to help kids better do that? Does that make sense?
Yeah, that's a really good question. Senna, if you don't mind, I'll go first. One thing that we had some good luck with, I have a colleague that many of you may know, Rob Quadden, who's a brilliant math teacher. And Rob was an 8th grade teacher. He's now working with the high school at Innovation Academy. Using some simple algebraic problems and looking at them as a stock flow really helped a lot of kids. Now, I don't know how widespread we could do that, but if you look at a problem of, algebra problem of, for example, the systems problems that have two different rates going on at the same time, and make a very simple, linear model with two stocks and see where they cross. So if you say, for example, a fox is chasing a rabbit and the fox is gaining on the rabbit, when will it overtake it or whatever? Kids like doing those kind of problems, and also they're relatively simple to do. So I think finding some linear models first always helps. Telling stories about population, I think the ones that Senna showed were really good. Sometimes we tell a little story about a fish pond and what happens to the population. So starting with very simple models is, I think, the way to go. But I agree with you. It's hard conceptually for kids, and adults, I think, have an even harder time with stock flows.
Yeah, thank you.
And like I can only add just a small part. I actually agree with all the points that Alan already mentioned. And also I think working together with the graphs. So when they build like one by one, those simple models and seeing all the effects of it in the graph. So it makes them like together with the stories, when they see the change of the behavior over time, they, I think, understand it better.
Thank you very much.
I'm sorry that I'm going to stop this right now. Please communicate with us if you would like to know more about what's going on. We have SIG meetings every other month to talk more about these ideas. I am going to now start playing John Darko's presentation. Please feel free to leave when you need to leave. He is not here to answer questions, but we'll play his presentation, and it's 15 minutes. And then after that, anyone who's still here and wants to talk, we're happy to stay on and talk with you. So I am going to share my screen. Trying to get this, share my screen. And trying to find my, yes. And John Darko's talks about climate change in a very simple way. One stock, an inflow and an outflow, and he does not have feedback. So it's a very, very simple beginning idea. And so I hope you'll find it interesting.
There is no voice right now.
Oh, okay. I'm sorry. I must have made a mistake. Let me stop. I will stop sharing, go back to sharing, share the screen, share the sound. Okay, we'll start again. Here we go.
I'm going to show you how I use climate change modeling in my classroom. This lesson that I'm going to do takes about 3 days, and my students have already created system dynamics models with Insight Maker before, but this is really the first main introduction to using Insight Maker and having them build their own models. So they're going to make this very basic model. First thing I do, though, is we just start off with paper and pencil. There's 4 goals I have for this lesson. Number 1, just how does carbon cycle? 2, what is the difference between an open system and a closed system? And really, the carbon cycle is going to be a closed system. Third, how do we operationalize our models? So scientists build equations into their models, into their computational models. How do we operationalize that? So they learn the skill of how to turn data, evidence, experiments. How do they use that information to build in mathematical operations for their model? And then lastly, how do they extend models? So how can they add parts to their model? Okay, so first things first, I have them look at this model up here where you have emissions, carbon in the atmosphere, and net removals. And then what they do with that is they try to complete these tables. So carbon in the atmosphere is 862 gigatons of carbon, and that was in 2018 approximately. So if our emissions, our flow to is 4, and our flow froms are 4, well, we have 4 minus 4 equals 0. And then how's that going to change the stock? Well, it's not really going to change this stock at all. So it's going to be 862. Next time iteration, it's going to be 0, so 862, and so forth. So they get to see, hey, this is a sustainable system. When your emissions match your removals, the carbon in the atmosphere does not change. Then we do this again. This time we have, instead of emissions being 4, we have emissions being 10. And so we have 10 going in and 4 going out. So 10 minus 4 equals 6. And it's not going to change. It's going to stay at 6, 6, 6. So then how is that going to change the stock? Well, 10 minus 4 is going to be 6, so it's going to go up 868, 874, 880. And so I walk them through to see, this is just like pencil paper simulation, and see how that works. So once they get to that, they're going to sign in to Insight Maker, save their model, and they're going to build this model and simulate it. Make sure it matches up with these two tables they did when they set the emissions and all the parameters, just like these two tables. They should get the same results, and that works out pretty successfully. I'm going to skip through some stuff here, like things like what are shortcomings of the model are good leading questions. But anyway, let's get to, is this an open or closed system? Well, it is definitely an open system. It's an open system because we don't know what the source is here, and we don't really care what the sink is. It's an open system. Did I say open system? Anyway, it is. It's an open system. Where is that coming from? We don't know. Where is it going? We don't know. So then what I like to do is have them go through and turn this into a closed system. And where do I do that? Let's skip ahead. There we go. So this is what their model ends up looking like, minus this cumulative total anthropogenic carbon dioxide. So they end up putting this like carbon in the biolithohydrosphere stock, bio for the biosphere, litho for like the Earth's crust where fossil fuels are and such, and then the hydrosphere, like our oceans. So this now is going to be a closed system. And they get to see how carbon is cycling. And very, very simple carbon cycle model, but it's a closed system. Carbon's not coming in from outer space. It's just staying within the Earth, but cycling through these different Earth systems. Okay. Then, so first, just build a simple carbon model. Second, see how it's a closed system versus an open system. Now I'm going to show you how I have my students operationalize equations of models. So we're going to look at temperature change, because in the carbon cycle, what we are most concerned about is not really how carbon is moving, but how that carbon is leading to the greenhouse effect, and how that greenhouse effect is leading to temperature change. So I have them, I got this graph from the IPCC. I like this one because it reports the gigatons of carbon versus just the gigatons of carbon dioxide, and it's just the same units I was using earlier. So I go through, have them look at this graph and have them see, kind of dissect what these different words mean: cumulative, total, anthropogenic, CO2 emissions, and then temperature, anomaly, relative, all these we look at. Ultimately, then they are going to add this variable to their model and come up for an equation for it. So what would the cumulative total anthropogenic CO2 emissions be for their model? It's a little more complicated than you might think at first. So let's see here. I'm going to skip over the directions so I can kind of show both things. But let's see here. There we go. So what we have is there are 862 gigatons of carbon in the atmosphere, and the cumulative in 2018 was 515. So let me draw this out. Here's your total anthropogenic carbon emissions as our variable. So, and this is the total carbon. So at the beginning of our simulation, time 0, we should have a total of 862 gigatons. So it starts off at 862. Now, if we're adding 6 each time, it's going to go up from 862 to 868, right? And so forth. Well, what is the total anthropogenic carbon emissions going to be? In 2018, it was around 515 gigatons of carbon. So whatever this equation is, at time 0, it needs to equal 515. So they need to come up with a formula, and I go over this kind of same way I'm going over it with you, except much slower. They need to come up with a formula that is going to equal 515 at the beginning of their simulation, and then is going to equal 868 at the next time interval if they're emitting 6, total of 6 gigatons each time interval. All right. Anyway, take some time. Some students really struggle with this, and ultimately some kids get it, and I have them share with the class how they develop their formula. I do say that I want them to incorporate. So let's see, they need to use this carbon in the atmosphere into their formula. So generally carbon in atmosphere, it's that stock minus the difference between these two. And I think it's 347. So what does that 347 actually mean? It means if there weren't any anthropogenic carbon, then there would be 347 gigatons of carbon in the atmosphere. But, so if there was the carbon in the atmosphere was 347, minus 347, your total anthropogenic carbon emissions would be 0. Some students figure it out, some struggle. It's okay, but this is our first step in operationalizing our model, that the students are building the formula themselves. And it's really neat to see how some basic math, it's not great, but you get to see how much kids have trouble with putting simple math into something useful, like building a computational model. Okay, So then students look at this graph and their goal is to figure out what is the cumulative total anthropogenic carbon. So look there, and what is the temperature at 0, which is going to be 0. And then what is it going to be at 2000? Well, we're going to look at two projections. We're going to look at this projection and the RCP 8.5. Well, they just draw lines up and try to figure out what that number is. This one I think is around 3.2. This one is about 4. What does it look like, do y'all? Yeah, let's say 4.2 for now. As long as we come up with some numbers that are similar, I'm good with that. Okay, so now that we have those two numbers, we can write them in our table. So this is going to be 0 and 0. This is going to be 3.2 and 4.2. Then they're going to figure out, well, what would the temperature be? Well, if we're going by this median induced warming, they need to again operationalize. They need to come up with a formula for the change in temperature if the temperature is 0 or if the temperature is 2000. What would, if the gigatons of anthropogenic carbon is 2000, what would the temperature be? Well, it's going to be 3.2. So how can I develop that into my model? Ultimately, what they're trying to do is you have point here, and let's see, 0, 0. All I wanted them to do is figure out what the equation of this line is, which, because you're 0, 0, it's just the slope. So it's going to be rise over run, 3.2 over 2000, which equals 0.0016 something times your gigatons of carbon. Gigatons carbon equals your temperature. And students did this. It's awesome to see them struggle, and then I give them a little more, try not to feed them that I'm looking for the slope, but I even tell them, I give them a lot of information to try to do this. But they are really trying to just, I want them to see that they can make these models, and they can use math to really develop a kind of sophisticated model. And they do the same thing for the RCP 8.5, which that equation is going to be something around, I think, 4.2 divided by 2000, which ends up being temperature equals 0.002 something times your gigatons of carbon. So it's really, the slope is steeper, right? And that makes sense. The RCP 8.5 was steeper than the median. And so this is like, as we talk about this is the climate sensitivity. This is what models are really trying to figure out as we look into the future. It makes a big difference. I have a bunch of questions that deal with our future and how that will affect. Let me bring up, let me bring up the Insight Maker model, and you can kind of see, all right, so right now it's at that median, median amount, lower projection, and we simulate this, and I have them put these graphs in. So here's temperature, and they should see what temperature would be after 100 years. And then I have them also do a scatter plot, which the scatter plot should mimic the same amount. Let's see. it should hit similar points as that graph from the IPCC. So the graph there, the points should kind of line up with that IPCC amounts, and they look and try to validate their model in that way, and it works out great. Okay, and then we can look. Oh, let me go back. Oh, I closed it. Then we go back and hit it to around 2, simulate, and it's a little more. Anyway, the last thing I wanted to show real quick is rats. Here's a student's model. It's hard to see, but they added things like plant more trees, increase electric cars, increase alternative energy sources, and how that would affect the different levers. Anyway, post resources. I know I'm a little bit over in time. Thanks.
Do we have, is that background noise somewhere? I think there's background noise. Sorry about that. I don't know how that's working.
No, there was no problem, Diane.
Yes.
There is no, yeah.
So
okay.
Can you hear, is now there's not this background noise? Yes. Sorry. Thank you all for coming. If you have any questions, I think Alan and Senna would be happy to stay for a few minutes to answer questions. Is that okay? But we thank you for coming, and we understand if you have to leave. But if you have questions, please feel free to ask them. We will stay for your questions, and then we will terminate the presentation.
Hi.
Yes,
okay.
Please.
Hi, this is Tanvi. I actually just said goodbye, but I think every time I was like, I'm going to leave now, it just kept getting interesting. And I was like, okay, I'm going to stay a few more minutes. So I mean, I'm not an expert in system thinking, and you guys, just the depth that you all had was really amazing. So I might have a question which might seem very obvious, but the thing is, when we make system diagrams for our kids in the games that we build, there are so many factors that are there in any system, right? So we have to make a choice in what are the systems that we want to select to be reflected in a particular system. And that's all right, because that's a choice that we make, that, okay, these are the key factors that we want to be reflected in here. But especially when the kids start asking questions, when they ask, but this affects too, and that affects too, how do you all address it? I mean, have you all ever had kids come up saying that, oh, but wait, doesn't this particular factor which has not been accounted for in our system diagram, how do you all deal with that? Or I'm sorry if this is a very basic question. Was I clear?
I think what you're saying is you have a lesson that deals with either causal loops or is it causal loops?
Yes.
And you've included some items from your story in your causal loop, and then they say, but what about this?
Exactly, yes.
And how do you include their idea in the causal loop?
Right.
Well, I might, if I couldn't figure out a good answer right away, I might say, well, why don't you get in groups and think about where you think it should be included? Or I don't know if this causal loop is on the board or on a paper, but to have them come up to the board if it's on the board and maybe they could talk in groups a little bit and have somebody come up and say how it would be connected, and then try to explain why they put it there. It's sort of a way to turn it back to them, but to let them have some time to talk to, in a small group situation, to talk to some of their friends in the class and see where they think it might be. The teacher doesn't have to have all the answers.
Yeah, of course not.
The idea is you could say, well, I don't know, where do you think would make sense? Would it, you know, that's a possibility. Alan and Senna, do you have some ideas?
I can also say like just a small thing. I think that's a really good solution to turn it back to the students and have their thoughts about it. Also, when you have limited time, or when you have so many ideas are coming up, you can always make the model bigger and bigger and bigger. There is no limit when you start growing the model. So sometimes it is also tell them that now we are looking at this frame, and all the cloths that you see on this part and this part are not involved in this frame. So every model has its own limitations, and this is the part that we are looking right now. But yeah, it's a really good point that we can connect it from this part or this part. But in the beginning that we said that we will focus on this part, that's why we didn't include it in the first place. So this is also another option to show them.
So setting the boundaries for the model. Mm-hmm. So essentially you're setting the boundaries for the model, saying, in order for people to understand the model well, we need not to have too big a model. And so we set a small boundary to begin with. And even though these other ideas are important, our boundary is small to talk about it and maybe to create the diagram. And it could be expanded at a later point if those became something that you would want to include in helping to fix the problem or something, but you got to start small. So I think that's a great idea, Senna. That's a really important point.
Yeah, and I think the idea of having competing interests from different points of view is important for kids to understand, and it helps them to, I think, engage with complex ideas. So for example, we have one that we talk about here in our local area, where there's a road that goes from the city up to the suburbs. And it was always very crowded, of course, at rush hour. And then it was expanded. A big construction project happened, and an extra lane of traffic was put on both sides. And at first, that really did relieve the traffic. But as we've learned over and over, then it attracted so many more new people that now the traffic is as bad or worse than ever. And so if we present to students, how do you deal with a problem like that? You know, it's hard. I mean, some people have to drive. They don't have any choice. Some of the public transportation is really poor. You know, people have jobs that they have to be there in the morning and drive home in the evening and all sorts of things. But, you know, asking good questions and moving toward a solution is better than saying to the kids, well, just start to outlaw cars, or, you know, things that are impractical. So when we were studying energy once, so many of the students said we should have electric cars and hybrid cars. And we said, well, go to the parking lot and see how many hybrid and electric cars there were. And at that time, it was just in the beginning when they were first being produced. I think there were just 1 or 2 out of about 40 or 50 cars. So having students think that, you know, you have to look at things from many points of view helps them deal with complexity.
Great, that makes sense. Thank you. Like, these answers come to you also easily, intuitively, and it really helps to learn from experience. So thanks for answering that, because
well, they're not easy, but believe me.
We've been doing this a long time, and it wasn't easy for us at the beginning either. And we welcome you to attend our SIG meetings, which are every other month. and we have more conversation at those times, and certainly can have more time to talk about specific
Absolutely
issues.
We're in touch with Gokshan, and she really keeps helping us, and she makes sure that I'm here every time. So you're definitely there.
Thank you. Thank you. Anyone else have questions for our presenters?
Diana, is it possible to share my slides if people would like?
Yes, I would like to figure out a way. We are revising our website, our web page on the System Dynamics Society website. And what we like to do, the videos, the recordings are on YouTube. I don't know if we can make download. I think we can make downloads at the YouTube site. But we also have access to all of our SIG and webinar recordings from the System Dynamics Society pre-college webpage. And there we can have downloads as well. And so I asked you, Alan, if you would be willing to share your slides. And I think you said that would be fine. And so, yes, we try to have other resources. So if you, I think you sent me, did you send, no, you didn't send me your slides yet, but we can communicate and make sure that your slides are available. Senna, did you want to make your slides available, or I don't want to put you on the spot.
Yeah, I already shared on chat, and we can also share it on the web page. Yeah.
Okay, good. I think that's nice, and we will make sure those are available for people. And having the recordings, I think, are also nice so people can go back. And if anyone wants to contact us, please, I think you can just respond to the emails that have been coming to you, right? As advertisement for this. We now are using MailChimp, so people can unsubscribe if they want, but this means we have a tighter list of people who are interested in what we're doing. So you can communicate with us that way. Any other questions? All right, thank you very much. We've gone over half an hour, but I think it was well worth it. It was exciting to see what's being done in the classroom. And sharing this information with each other will help us spread this, which I think is extremely important in the K-12 arena. Thank you for coming. I apologize for being late, but it was pretty exciting to hear the presentations. Bye.
Thanks so much.